This video continues our discussion on NMR. In addition to gaining valuable information from the number of signals and the chemical shifts, it is important to also look at integration. Integration is the area under a peak, and it quantifies the relative number of protons giving rise to that signal. This shows an example spectrum where a step curve is measuring the area under each peak. So if we look at these integration values, these are approximately the same, and these are approximately the same. So the signal here and here, those two signals represent the same number of protons, whereas the signals here and here also represent the same number of protons. Now, as the computer operator, you can set one of the signals to a whole number and let it represent a number of protons. So for example, you could set this signal to 1, and then everything else gets adjusted accordingly. So here, this signal also would represent 1, and then this signal would be 1.5 times that of the reference signal. Integrations represent number of protons, so if you have a fraction, you should adjust those values to whole numbers. So here, everything was doubled, which took this value to 2, and this is 2.10, and then these values are approximately 3. Now, what do those integrations represent? They represent relative quantities of protons, and it's important that we use the term relative because they're relative quantities, not absolute quantities. And symmetry can also affect integrations. So for example, if we look at 3-pentanone shown here, it has 2 protons. The protons in blue, all of those blue protons are equivalent to each other, so they give rise to one signal. And then the hydrogens in red. All 6 of those are chemically identical, so they give rise to one signal. So we would have 2 signals. So the relative integration between the blue to red protons would be 2 to 3. Now the absolute count of the protons, you have 4 of the blue protons and 6 of the red protons. And 4 over 6 is the same as a ratio of 2 to 3. To determine the absolute ratio, not just the relative ratio, you need to know the molecular formula. So, for example, if you know the molecular formula for 3-pentanone shown here, then you know that that relative ratio of 2 to 3 really represents absolute ratios of 4 to 6. Here's a proton NMR spectrum of the molecule CH3OCH2Cl. It shows 2 signals, and I want you to determine which hydrogens correspond to which signal. So does the signal at 5.46 correspond to the 3 hydrogens of the CH3 group or the 2 hydrogens of the CH2 group? Then notice the integral values of 1 and 1.5. What do those numbers mean, and are those absolute or relative values? And explain your thoughts in the chat. The final important characteristic is the splitting pattern, also known as multiplicity. This is the number of peaks in a given signal. If it's just 1 peak, it's called a singlet, 2 a doublet, 3 a triplet, 4 a quartet, 5 a quintet, 6 a sextet, and 7 a septet. And then also, people will often use the term multiplet for things above a quintet. The cause of splitting patterns is due to magnetic effects that protons have on each other. So let's consider protons A and B shown in red and blue. They are color-coded to indicate that they are not chemically equivalent, so they will give rise to different signals. Now, if we're looking from the point of view of HA, the red proton, it is going to be affected by the magnetic field, by the external magnetic field. So for HB, its neighboring proton, HB can be aligned with the field or against the field. This means that there will be 2 different magnetic environments for HA, and as a result, this appears as a doublet. So if HA is in a molecule where HB is aligned against the field, then it experiences a slightly reduced external magnetic field than if HA is in a molecule where HB is aligned with the field. So as a result, HA is experiencing two different magnetic environments. Now let's consider the example from the point of view of HA, where it has two neighboring protons, HB. So here HB, there's two of them, and they're both blue, so they are chemically equivalent to each other and will give rise to one signal. Now HA will be coupled to both HBs. However, there are three different scenarios that HA could experience. Both of the HB protons could be aligned against the field. One could be aligned with the field and one against, or both could be aligned with the field. So as a result, depending on whether HA is experiencing this scenario, or that scenario, it will experience a slightly different external magnetic field, and therefore it will show up as a triplet. Now notice the height of the triplet is 1 to 2 to 1. This is 1/2 the height of this, and this is 1/2 the height of the middle as well. That's because statistical distribution of these three scenarios is 1 to 2 to 1. Now consider a scenario where HA is split by three neighboring atoms. So what are the different scenarios? All three HBs could be against the field. All three could be aligned with the field. Now, these two in the middle, you could have one with the field and two against, or you could have two with the field and one against. So that means you're going to have a total of 4 different magnetic environments that HA can experience. And as a result, you get 4 peaks, which is the quartet. Now the height of these peaks is 1 to 3 to 3 to 1. And that's because statistically the distribution is there's one scenario here, 3 different scenarios for the middle ones, and one scenario for all 3 being with the field. So by analyzing the splitting pattern of a signal, you can get information about the number of neighboring equivalent protons on adjacent carbons. And this is where we get the N+1 rule, where the splitting pattern is the number of neighboring equivalent protons plus 1. So in that last example, there were 3 neighboring protons, and we got a quartet. So 3 plus 1 is 4, hence the quartet. There are 3 key rules for splitting. Number 1, equivalent protons cannot split one another because they resonate together. 2, to split each other, protons must be within a 2 or 3 bond distance. So if we look here, splitting is observed between HA and HB. So between HA and HB, there's distance, but the distance between them is 2 bonds. Between HA and HB here, it's 1, 2, 3 bonds. So 2 bonds, 3 bonds. Between the HA and the HB here, it's 1, 2, 3, 4 bonds apart. So splitting is generally not observed because those are too far apart. The third key rule is that N+1 rule is very simple, and it only applies to protons that are all equivalent. So the splitting pattern observed for the proton shown in red here will be more complex than a simple triplet because it will be coupled to this proton and to this proton, and these are not equivalent to each other. This would give rise to complex splitting, which I will briefly discuss later. But I will focus primarily on simple splitting. The degree to which a neighboring proton will couple to its neighbor is called the coupling constant, or the J value. And this is the distance between the peaks in a signal, and it's measured in units of hertz. And protons that split each other will have the same coupling constant. So HA couples to HB with the same coupling constant that HB couples to HA with. So if we look at the quartet and the triplet, these coupling constants are all identical. Higher field strength instruments will give better resolution between peaks because the coupling constant is a smaller percentage of the overall Hertz available. So the peaks here on the right, that is what you see from a 300 megahertz instrument, whereas the overlapping peaks here are due to a lower field strength instrument being used. There are recognizable splitting patterns that should stand out to you in a spectrum and indicate the presence of certain groups. An ethyl group, for example, will give rise to a quartet and a triplet. The hydrogens in red are coupled to the hydrogens in blue, and they will show up as one signal that's a triplet because the neighboring blue protons, there's 2 of them. So using the 2 + 1 rule, we place in 2 for N and we get 3. If we look at the signal for the blue protons, they're coupled by the protons in red, and using the N + 1 rule, we put in a 3 for N, 3 + 1 is equal to 4, we get a quartet. And the triplet and quartet must have the same coupling constant if they are splitting each other. So if we look at this, you may be tempted to think it's an ethyl group, but notice the spaces between the peaks, they're definitely not the same. So it can't actually be due to an ethyl group where the protons are splitting each other. If you see a singlet with an integration equal to 9, that suggests the presence of a tert-butyl group, because all of those hydrogens in red are chemically equivalent to one another and they aren't coupled to any neighboring protons. An isolated isopropyl group gives a characteristic doublet and septet. So here we see these methyls, so that gives rise to a signal corresponding to all 6 of those blue H's, which are coupled by the one red neighbor. So here we see that as a doublet, but the one red hydrogen, from its perspective, is coupled to the 6 blue hydrogens,